Hi folks, this is the third video segment that I'm making for linear dynamics in Catia. The one that we did, there were two that were already done. One was a lump parameter system, two masses and two springs, and there is very limited post-processing capability that you can rely on in Catia for that. And then the second was the stress wave propagation, and uh, which was modeled with beam element. So this is a third one. It is a simply supported beam, which is loaded at this point with a harmonic type of loading. Okay, the details of the geometry and this frequency is given here. I believe this frequency is assumed to be the frequency of the applied load is 7 pi radians per second, or 3.5 hertz. Now, we're going to be monitoring the displacement at the mid-span location, which is right here, and there is a closed-form analytical solution for this using separation of variables that is written here. And if you look at that particular midpoint location, I have plotted the variation of this vertical displacement as a function of time, and it's right there. Of course, this is an infinite series, but we have to truncate it for plotting purposes at, for example, I've done it at three terms. But if you go to more than 3 terms, you see that there's very little change that appears in this graph. Okay, so we're going to be solving this problem. Now, I also want to point out that this problem probably is more suited to do as a harmonic response problem. Okay, however, we're not doing it like that. We're going to actually input the time variation of this sinusoidal or cosinusoidal harmonic load in an Excel spreadsheet and read it in. Now, also, this particular problem is more representative of structural dynamics problem as opposed to the one that we had on stress wave propagation. Okay, no damping, right? All right. So there are some issues that are going to arise here, and I'm fully aware of that, but we're going to discuss it as we go along. Okay, so let's start with the Catia part file. Right there. All right. Now, before I do the problem, let me make sure my units are set as the units that I want. So tools, options. Let's see. Okay, so the length is inches. Time, I'm going to change it to seconds. Seconds. Okay, we don't have a distribute lump mass here. Density is set as inch per inch cube. Force is pound, and I think that's okay, area inch squared. How about that? Although it's not necessary to do this, you can input any unit that you want. It's going to get converted. So yeah, that's good. All right, we're going to use beam elements. So first thing that we're going to do is we're going to in a sketch we're going to draw a line. Here's on that vertical plane. I'm going to sketch, and all it is a line which is 20 inches long. Right there. Okay, let's make that thing 20 inches. Good, exit. Now, let us make sure that we join this thing. If we don't join this, later on when we try to mesh it with beam elements, it's not going to work. And very frequently when I do these video clips, I forget about that, then we realize that we have to go back and join it. No problem. Now, I'm going to create 2 points. One of them is exactly at the midspan. This is where monitoring is going to be done. So that's 10 inches. And the other one has 5 inch location where the load is going to be applied. Okay, good. So let's make this thing out of steel. And and change the values to meet whatever I have in my mathcat sheet or PowerPoint sheet. Okay, so there's only two minor changes that we have to make in the values. The default property for steel in Catia Young's modulus is 2.9 times e to the 7. We're going to make this 3. That's what I have in the PowerPoint. And then this is the unit of density, or the value of density 7.355 in default database. We're going to make it 7.4. That's pretty much it. All right, so let's save this thing. File, save management, save as. Okay, desktop, simply supported beam right there, and it's going to go in that folder. Okay, then we're going to go to generative structure analysis. Remember, we want to do ultimately a transient dynamics problem, but my suggestion in the first video segment was to start with the statics, and of course later on you have to do frequency because that's what's needed in the linear dynamics case. So static, fine. Now, we need to mesh this. The problem is that if we try to mesh it with beam elements here, look, this is what we got, and there is not the options that we have here where we can make sure that these points that are created are actually in the model. So I can't do it here, so we have to switch to the advanced meshing tool to be able to do that. So here's the beam. Notice that now I have some additional options here. So first of all, we're going to select the support, and 0.5, okay, that'll give you about 20 elements, maybe 40 elements through the length. And then I want to make sure at isolated point, I want to make sure that this point and that point, they actually become part of my finite element model so that we can apply loads on it. Very good. Let's apply our cross section. This is a beam problem. So the cross section is a square 1 by 1. So what I'm going to do is actually I have to go back and create an orientation point here. It's something that I forgot to do. So let's go here, and in the y direction I make something. Well, this dimension is quite arbitrary, but I'm going to be using this thing as my orientation point. So all right. So where is the? This is the advanced meshing tool. So we've got to go back to generative structure analysis. Here is the 1D property, and I want it to be a rectangular, dimensions 1 by 1, because 1 by 1 will give you 1 square inch and 1 over 12 for I, which is exactly what I have in my mathcat sheet. Okay, so let's see now. This the orientation point is right here. The support is that beam. You can see that this is a 1 by 1 square, which because of that orientation point is oriented properly so that we can do the problem. All right, good. Now let's do the restraints. So what I suggest is the following. I want this thing to go up and down, and of course bend about the y-axis. So this endpoint is going to be pinned, but still free to move up and down. No, it's a pin, so it cannot go up and down, but it can still rotate. That's what simple support means. Okay, so that point. All right. This other one, I'm going to leave it as a roller. The roller means that it can move in the x direction. And notice that this is the kind of thing that I have here. Okay. All right. Then we're going to apply a static load at that location. 100 pound downward, negative right there. And you say, okay, if you zoom in, you see that there's a load here. Okay, let's save our analysis file. So we go File, Save Management, Analysis, Save As, in that same folder. Okay, very good. Okay, we can run it. nothing fancy here. Hang in there. Something is not quite done yet, so we meshed it. Properties are given. Static case. We put restraints. Okay. We put a load. All right. Should be able to run this. Run all. Okay. Nothing fancy is going to happen. This is going to deflect downward, which means that if there are any errors, we would have probably spotted, at least the obvious one, we could have spotted it here. So this is where the load was applied. This is downward displacement. I'm not going to be able to plot these things in the contour form because my graphics card doesn't support it. All right, good. Now this is done. So now we're going to insert a frequency case. Okay, so insert frequency case. Now it's not going to be the restraints. We're going to use the same old ones. So restraints, we're going to use this restraint that we had here. Okay, good. And default is giving you 10 frequencies. So we just live with that for now. Run it. And let's look at the frequencies. Now notice that some of these are bending, some are axial. So this one is bending, this one is bending, this one is axial for sure, okay? And this one was axial. So keep in mind that these 10 frequencies, not all of them are appropriate for the kind of thing that we want to do for bending mode. But anyway, let's leave it the way it is. We're not going to worry about it right now. Now, once this is done, we save. Save. Where's the save? Right there. And then we're going to insert a transient dynamics. Okay, as far as the frequency case is concerned, we're gonna use the same one that we did. It's right here. It's a load excitation. All right. Now, what have we got here? First of all, notice that load excitation. If we try to do this, it says what is your selected modulation, and we don't have one. So first thing I have to do is I have to go and create an Excel file with the kind of load that I have reflected there. So let's go here. Let's go to my folder, which was simply supported, right there. I'm going to make a Excel file and put it there. Where is it? So let's do this thing over a 1 second interval, okay? Let's do it over 1 second interval. So just give it 1 second. Where is Excel? Right. First column is going to be the time. Okay, so X is in second, and the second column is just some non-dimensional, value which represents the amplitude. Okay, so here let's start with 0 and point let's see now, 0.01. And we go 0.01, so this is going to be, let's drag it all the way to 1. What have we got here? Well, that was more than 1, so we go up and we stop at that. Okay, so let's go up here. So this is 1 second. Right there. Now we're going to write our formula for the load. So this is equal to cosine of parentheses 7 pi 7 times 3.14152 times times this thing, which is time. We close it, we hit return, and basically drag this thing together for the other entries. Right there. Very good. So we're going to save it, file, save as, desktop, and it was simply supported something right there. Yep, I'll call it book 1. Okay, good. So now we can close this. Back to Catia, analysis, double click on load excitation. It says what is the load. The load is going to be the same static load that we applied, and remember it was 100 pounds downward. And what is the excitation or the modulation? The modulation is that curve that we just created, which I forgot to actually import it. Okay, so we're going to do this thing again right here. See that? Under modulation, this is time modulation. It says where is it? Well, browse. It was in that folder. Yep, it's right there. This is the step I always forget. I have to go back and do it. Okay, so just give it 1 second. Alright, so it is right here now. We can pick it. So back to that load excitation. For selected load is going to be that load that we have in the static case. For modulation, now we go and select this guy that we created. And the factor is 1 because I applied 100 pound downward. So I don't have to scale that up or down, so just leave it the way it is. Alright, now the last thing that we have to do here is to say how many seconds do we want to do this thing for. Let me make this thing for 1 second, okay? 1 second. And how many steps, how many intermediate calculation we want to do as far as Duhamel integral, so let's get 200. Alright, good. I think we are pretty much done here. So before we run it, let's save this. Where is the save? Right there, there's a save. And we run it. And it's done. So put the cursor there, right click to the display. Let's plot only one curve, which means the displacement only. It says go pick your node, so we go and pick this node here. This is where we want to modify. We want to monitor. Now I believe that. Let's see. Now I don't think I can do it from here. But what I can do is I can say, where is my model here? The model analysis is right there. Why don't we actually look at our mesh? Let me close this for a second. Okay, right there. I can get it from here. So let me hide that. All right. So I believe it's node number 4. I believe it's this one. So let's go and create our. Let me delete this. 2D generate 2D display. Next, finish, and select that node number 4. From the screen. Was it this? Yeah, add, and we say OK. All right, double click on it. There's my graph. Now a couple of things you have to know is that this, look at the units first of all. This is meter. I don't want meter. I want the units that I specified, which is inches. So you select this, right click, options. Okay, where is it? Let's see now. Options. Just a second. And so, okay, yeah, here's what I did. I keep forgetting this. You put the cursor in the white area, right click, options. I don't want MKS, I want the option that I specified, which was inches. So notice that first of all, now this is in inches and this is in seconds. Okay, The other thing is that what you have, these are all positive values. You can see that. This is actually the amplitude. So what I don't want is, I want to put the cursor, you see this on this axis, on this vertical axis, right click, format. I don't want amplitude, I want select real. Real means give me positive or negative numbers. There we are. Now this is supposed to be that. Okay, this is supposed to be this. However, there's some wigglings here which needs to be accounted for. And the reason that this is happening, notice that we are solving a dynamic problem, transient dynamic problem. And we are saying that suddenly the load is cosine of whatever, 7 pi t, 100 cosine of 7 pi t. That's impossible, because suddenly means t equal to 0, and immediately we have a load of minus 100 pounds applied there. So let me show you a trick to get rid of this thing, these wiggles. Okay, so here's what we're going to do. We're going to go to our Excel spreadsheet. The first, let's make the first maybe 10, the first 0.1, okay, the first 0.1, or I don't know, actually the first, let's say 0.05 seconds, okay, make it grow linearly. So I'm gonna delete all of these things, okay. I'm gonna delete all these formulas. Okay, so let's drag this thing. I'm gonna delete that. So this is equal to let's say 10, and where I get 10 is, let's say the first 0.1 second. The first 0.1 second times that. Hit return. And then drag this thing, go all the way to 0.1. So you can see the first 0.1 second, the load is applied linearly, okay? And at this point, my cosine will disappear. So so this is going to be equal to cosine parentheses 7 times 3.141592 times, so this is really my new starting point. So it's going to be this minus 0.1 close and close. Okay, so now I'm going to take this and drag it all the way to the time that I want to go. I don't know, if you want to go all the way to 1 second, that's fine, just leave it there. And save this, close it, go back to analysis. Okay, let's get rid of this graph. And let's get rid of this this modulation, because our modulation is a new one that we have created. So insert the new one, that's this one. Okay, and let's go down here, double click on the load excitation. Notice that because we deleted the first one, it says I don't have one, so just go and select the one that we just imported. Okay, and run it. And then look at the results. You see, there is no, that was a non-physical oscillation that we had here, because it's impossible to make a load suddenly appear as cosine when t is 0. You go from 0 to 100 pounds in no time. So first I loaded it up to that value, and then cosine is used here. Okay, that's pretty pretty much it. By the way, these things you can export it. So let me see if I can do this. Export data. Let me see. Select data. Not there. Where do we get this thing? So let's go down here. Where is the analysis? Let me see if we can export something. Yeah, it is possible. It is possible to take these things that you just generated and send it in an Excel file. At this point, I don't remember how to do that, but I'm sure if you look at it, you can figure it out yourself. Let me try one more time, see whether it can be done from somewhere here. Select options. Nope, that's for the location. Let's see, from select. I don't think these are the ones. Let me select this. Ah, there. Okay, you have to actually select the curve. The curve, right click and export data. It says where do you want to put it. So desktop, Excel folder, and this is called exported data. Exported, I'll say simply supported because there's another thing there. Okay, let's go and check it out. So it might be two columns. One column is time, the other one is the displacement. Yeah, and then you can create your own graphs, things like that. I hope this was useful. We'll do some